All right, guys, let's continue our study of the rational function. Let's go back to some previous types of families of functions that we've talked about. And let's think about the domain and which values of x would possibly be not counted in the domain. Okay, would anything make the function undefined? So let's go back, way back. Example A here, this is obviously a linear function, mx plus b form. And the question is there any value of x for which 2x plus 3 would be undefined? Okay, and the answer is no. Okay, this one, the domain, is going to be all real numbers because you can get a y value for any x value. Okay, x can be anything. 2 times x plus 3 will always be defined. Okay, and then the next family of functions that we studied was the quadratics, right? So something like 2x squared plus 3. Okay, is there any x value that would make 2x squared plus 3 become undefined? And the answer is no. Again, this one, the domain is all real numbers because you will always get an answer. You know, if you plug an x value into 2x squared plus 3, you're always going to get a real answer out. Okay, we finally saw some in the last unit that did not have all reals as their domain. And if you think about the square root of x minus 3, okay, and the deal is since it's underneath the square root, we know that we cannot take the square root of something negative, right? So x minus 3 is the expression under the square root. It must be greater than or equal to 0, which means when you add 3 to both sides is that this thing is only going to exist for x values greater than or equal to 3. Okay, and if you think about its graph and go back to what we learned about transformations, we know that this graph would start out shifted to the right 3 units and then kind of continue that way. Okay, and notice there is no graph for x values less than 3 because they would cause you to have an unreal, right, or an imaginary y value. Okay, our new function that we just started on, the whole rational functions, when you have that variable in the denominator, this introduces another way of making something undefined. Two of the big ways are having negatives under square roots, which we saw before, and now in this case, we can never have a 0 in the denominator of a fraction, right? You cannot divide by 0. So what that means is x minus 3, since that's the denominator, we're going to have to say that cannot equal 0, which means that x cannot equal 3. This is the domain of that function. Okay, if you plugged in 3 for x, you're going to end up having 1 over 0, which is undefined. Okay, any other value for x works. Okay, and we're going to see what does that mean about our graph, you know, how does that look, and how do we handle it in this section. All right, so let's take a look. This is the basic parent function for, again, this whole family is called rational functions. The parent function is always the simplest case. You know, there's no transformations. It's just a basic straight up example. Okay, so for rational functions, the parent function is 1 over x. Okay, the thing that makes it a rational function is that the x is in the denominator, so this is as basic as it can possibly get. So let's think about what does it look like. Okay, and a good idea sometimes when you don't know what a graph looks like is to just make a little table, and you know, sometimes you can choose certain x values. Let's just choose values, a couple on either side of 0, and see what this guy's going to look like. Okay, so the function, the equation is y equals 1 over the x value. So 1 over negative 2 would just be negative 1/2. 1 over negative 1 would just be negative 1. 1 over 0, here's the interesting one. This is going to be undefined. Okay, if you're doing this on a calculator, it's going to say error. Okay, because we can't do 1 divided by 0. Okay, 1 divided by 1, 1 divided by 2. Okay, so let's plot some of those points. I'm just going to try to approximate here. Negative 2 is at negative 1/2. Negative 1, negative 1. 0 is undefined. 1, 1. 2, 1/2. And let's just think about what ends up happening. If we were to keep going, you know, if you were to do 3, for example, it would be 1/3. So it would be a little bit lower. Then 1/4. Then 1/5. And they end up just getting smaller and smaller, as we saw in the example yesterday, and they just get closer and closer to 0. You know, imagine it would be 1 over 10, 1 over 100, 1 over a million. But it's never going to quite get to 0. And then what ends up happening is you get closer to an x value of 0. Okay, we can't get to x equals 0, right, because it's undefined. But this graph kind of just curves up towards it, and we get a similar kind of thing going on down here in the third quadrant. And that's because, again, x cannot equal 0, so we get what's called a asymptote. Oops, it's supposed to be right on the y-axis there. At x equals 0, we have what's known as a vertical asymptote. And what that means is that is a spot on the graph. It's a value that the graph will approach. It'll get close to it, okay, but it can never quite get there, right? We cannot have x equals 0. X could be 0.1, x could be 0.001, right? It can be really close to 0. X just cannot ever equal 0. Okay, we also have in this example, as we go in the horizontal direction, we have an asymptote at y equals 0. Okay, that is a horizontal asymptote. And the reason that one exists is because as x gets very, very big, right, think of the function 1 over x. As x gets big, x is 100, x is 1,000, x is 1,000,000. Okay, the y value is approaching 0, right? If you put 1 over a huge number, right, the whole fraction is gonna approach 0. It's never quite gonna get there though, okay? So the x-axis and the y-axis in this case are both asymptotes for the parent function, right? Now let's talk domain and range real quick. We saw in the warm-up a little bit about the domain. So the domain is asking which x values are possible. So the domain of this thing is really all real numbers except that x cannot equal 0. Okay, because again, it goes back to having to divide something by 0, which is undefined. Okay, so the domain goes back to that. Now the range, which y values would this go through, I should say. Okay, the y values, if we kind of let me highlight a little bit. The y values here tend to get closer and closer to 0 and then go up to infinity. Here they're close to 0 and they're going down towards negative infinity. So they're going through every y value except 0 as well. Okay, so the range is that y cannot equal 0, and that's because we have this horizontal asymptote there. So these asymptotes tie directly into the domain and range of these functions. So as you're thinking about those, make sure you're making that connection and not treating them as separate things. This one, okay, being right at 0 on the y-axis and right at 0 on the x-axis, we're going to have the two, see the yellow highlighted? Those are called branches. It has 2 branches to it. And they're all right, so let's graph one and see what we can do. And let's think about the transformations like we learned about earlier in the year, where we have kind of stuff going on inside the function, outside the function, that kind of thing, okay? So we're going to find the asymptotes and intercepts first. So let's think about, here's the parent function that we just looked at. We know that one has asymptotes on the y-axis and on the x-axis. If we think about the shifting that's going on, we can figure out where the new asymptotes will end up. Okay, here's what I mean. I see a -4 transformation on the inside of the function, and I see a -2 outside. Okay, and the reason I know the -4 is inside, because on the parent function, it's 1 over x, the x being in the denominator, so anything plus or minus down in that denominator is going to be considered inside the function. So I know, and we should know, that a -4 on the inside is going to shift the graph to the right 4 units, and the -2 on the outside will shift the graph down 2 units. Okay, so here's my advice. Think about the asymptotes. Let's just shift those guys and then we'll try and get the graph going a little bit. So for our vertical asymptote, instead of being at x equals 0, it is now going to be shifted to the right 4 units. So it's going to be at x equals 4. Okay, and if you think about that, when x equals 4, if we plugged a 4 in right there, it would give us a 0 in the denominator, right? And that would make the expression undefined. That's when you get a vertical asymptote. Okay, the horizontal asymptote normally would be y equals 0, but again, we have this -2 shifting everything down 2 units, so it shifts the asymptote down 2 units to be at y equals -2. So the negative sign there, okay? So once you have that set up, you kind of have a good idea now where the graph's going to be. We're just going to fit inside of those asymptotes. Okay, now what we can do, we can get a little more accurate by plotting the X and Y intercepts if we wanted to do that. So let's kind of recap how we might go about finding those. So to find, it doesn't matter which one you do first. Let's say we want to just find the X-intercept. Okay, the X-intercepts, those always occur when y equals 0. So we're going to set y equal to 0 and see what happens. Okay, so the equation is y equals, so I'm going to put 0 equals, and then the expression was 1 over x minus 4 minus 2. And we're going to try and solve this for x. Okay, so I'm going to add 2 to both sides. Okay, so 2 equals 1 over x minus 4. Let's multiply both sides by x minus 4 to get it out of the denominator there. We can distribute the 2, and now we can go about solving for x. We will add 8 to both sides. And finally divide by 2. X is going to be 9 over 2, also known as 4.5. Okay, so that's our x-intercept. So 4.5 will just give us a little bit more accuracy on the graph. I know there's an x-intercept right at 4.5. Okay. Let's go ahead and find the y-intercept, and then we'll finish up our graph. Okay, so the y-intercept is always found by setting x equal to 0. So we're going to set the x equal to 0. Okay, and the expression was y equals, I'm just going back to the original expression, 1 over x minus 4. X is 0, though, 0 minus 4. And we're just going to try and simplify this here. Okay, so 1 over 0 minus 4 is negative 4. And then we have a minus 2, so we're at negative 1/4, and we take away 2 more, so we're going to be at negative 2 and 1/4. Okay, let's go back to the graph. Where is that? Negative 2 and 1/4 is just past negative 2. It's going to be hard to get that accurate, so let's just try and plot it as best we can, I guess. Right about there is going to be our y-intercept. Okay, so now we have a couple points on the graph. We got the asymptote set up. Make sure you do that first. Then you can get your intercepts. And now as far as sketching the rest of the graph, I mean, it's kind of a pain to plot a bunch of points and stuff like that. So if you want to maybe just use like a Desmos or something, but generally they're just going to fit within those asymptotes. Okay, and going through the points we had. So we're going to have something kind of like this. And again, I don't need extreme accuracy here. These are not easy to graph by hand. I'm more interested in us knowing the intercepts and where the asymptotes are than being like perfectly accurate with the graph. Okay, so those black branches there, those are the actual graph of this function. Okay, so we should definitely know where the asymptotes are. We should know where the intercepts are. Let's finish this up by stating the domain and range. Okay, which should be easy once we have the asymptotes set up. So the domain and the range. Okay, so if we remember, the vertical asymptotes go directly with the domain. Okay, so if there's a vertical asymptote at x equals 4, that means that the domain is all numbers except 4. Okay, if you look at our graph, it's never going through an x value of 4. It goes through everything else. Okay, our range is going to go directly with the horizontal asymptotes. If there's a horizontal asymptote, it means the graph ain't going through it. So at y equals negative 2, so that means our range is y cannot equal negative 2. Okay, now there are sometimes complicated graphs that have multiple asymptotes where it might cross through, but for the most part, an asymptote will not be crossed.